And our last speaker for today, David Rabouin.
Donc je vais dire quelques petits mots en français, puis après I switch to English after that. Donc évidemment je suis très honoré et très ému d'avoir participé à cet événement et puis d'être devant Eberhard pour le remercier de tout ce qu'il m'a appris, tout ce qu'il nous a appris. Je ne vais pas être long parce que ça prendrait toute la conférence, mais voilà, Eberhard est un maître pour moi, comme pour beaucoup de Leibniziens. Et j'ai choisi de parler d'un sujet sur lequel il a beaucoup écrit, l'infini chez Leibniz. So I switch to English. And so I will try to present some work on infinity in Leibniz. So I cannot in 30 minutes present like the complete picture of infinity in Leibniz. It's not possible. But I will focus on a few points. And fortunately for us, Leibniz prepared a list of meaning of infinity that he planned to send to DeVos. He did not send it, but it's very useful. So we have this note that he crossed out after he didn't send it. And so he said that there are 4 types of infinite. There is the categorematic infinite, that is a passive power having parts, namely the possibility of further progress in dividing, multiplying, subtracting, or adding. It looks like the potential infinite, but I will discuss this later. It looks like it. There is also an hypercategorematic infinite, or potestative infinite, an active power having part as if it were eminently, but not formally or actually. It's a little bit mysterious, but in fact it's the absolute. The absolute. So this infinite is God himself. But there is not a categorematic infinite, that is one having actually infinite parts formally. There is also an actual infinite, in the sense of a distributive whole, not a collective one. Totius distributively, not collective. Thus, something can be stated of all numbers, though not collectively. In this way, it can be said that for every even number, so here we are, there is a corresponding odd number and vice versa. But it is not therefore accurately said that there is an equal multitude of even and odd numbers. So in this talk, I will concentrate on the first and the last one. I will leave this one, which is for metaphysics, which is about God. And I will not talk much about the categorematic infinite, because the categorematic infinite does not exist. There is no categorematic infinite. Eberhard has published many papers about this question. Here is one of them that you can read, and in which he explained that in fact Leibniz had this idea of categorematic infinite, which is based on the idea of indefinite smallness or infinite largeness. And so here is the summary, as Eberhard likes to do at the beginning of his paper or at the beginning of his conference. Here are the theses that he wants to emphasize. Leibniz gave an exact definition of indivisibles and had a clear idea of what they are. He taught how to operate with them. Neither Galileo nor Cavalieri thought that they were infinitesimal quantities, and here the important word is quantities. For Leibniz, indeed, an invisible was an infinitesimal quantity of indefinite size. He defined exactly what that means. Leibniz elaborated his conception of the infinite based on the notion of quantity in a conscious departure from Galileo's concept of the infinite based on the notion of non-quantities. I call this concept the quanta concept and the non-quanta concept of the infinite, respectively. So let me summarize very quickly the arguments which are developed in the paper by Eberhard, and which are consensual amongst Leibniz scholars. So Leibniz rejects the idea of an infinite quantity, be it an infinite number, an infinite magnitude, doesn't make any, or an infinite connection, doesn't make any difference, because the notion of an infinite whole, in the sense of a totum collectivum, involves a contradiction. And he has many arguments for that. One of them is related to Galileo's paradox, what is now called Galileo's paradox, but he has other arguments based on the quadrature of the hyperbola. But he departs from Galileo in that he thinks that one can deal with infinite in the framework of quantity. So they are not quantities, but there is a quantitative approach of infinity, And so it's not like Galileo and Cavalieri who thinks that they are non-quantities. Not quantities. And this relies on the fact that the tools talk in terms of infinite quantities or infinitely small quantity can be explained in terms of indefinite quantities. This is where the syncatégrammatique will enter. Indefinite quantities can themselves be explained in terms of variable finite quantities. In this sense, infinitely small and infinitely large quantities are just fictitious entities, they are fiction, ways of talking of variable finite quantities. So that's a summary of the position that are explained by Eberhard in this paper, and which in fact are the ones that Leibniz will explain all of his life. And this is what he calls the syncatégrammatique infinite. So here is a famous quote from the Nouveaux Essais in 1704. It is perfectly correct to say that there is an infinity of things, that is to say that there are always more of them that can be specified. But it is easy to demonstrate that there is no infinite number, no infinite line, or other infinite quantity, if these are taken to be given wholes. And here, of course, the emphasis is on collective whole. The scholastics were taking this view, or should have been doing so, that's a very important point, I will come back to this, when they allow the syncatégrammatique infinite, as they called it, and not a categoric one. So here we see why we refuse the categoric infinite. The true infinite, strictly speaking, is only in the absolute, which precedes all composition and is not formed by the addition of parts. This is the hypercategorematic infinite. This is the only absolute infinite. The other one are relative infinite. But it would be, and it's a little bit late after, but it would be a mistake to try to suppose an absolute space which is an infinite whole made up of parts, precisely for the reasons. There is no such thing. It is a notion which implies a contradiction. So that's very important. And these infinite wholes and their opposites, the infinitesimals, is very clear, have no place except in the calculation of geometers, just like the imaginary roots in algebra. So the argument that Eberhard developed in the paper was based mainly on this edition, on this book that he published in 93. So it was already a question of this book before. We were fortunately enough that it was translated in French very early, 2004, compared to other language. And also the proof, the key proof is explained by Eberhard in this paper, which is a very important one. And it's true that in this book we find for the first time something that was not very well known before, that is to say that this idea that Leibniz defending the position that infinitesimals, infinitely small, infinitely large are fictions, in fact, dates back from this period. And it was not very well known before, and here is a key passage in which Leibniz said that. I will not read it, but you can see that it's exactly what he will repeat later. And here we are in 1676. And why was it very new? Because the story that was told before, the story that I learned when I was a student, was that in fact Leibniz was more like a pragmatic thinker. He didn't care much about the foundation of different calculus. It was not something that he was very interested in. And he was in a little bit forced to take position because of the quarrel in the Académie des Sciences, in the Académie Royale des Sciences at the turn of the century. And it is in this context that he created the idea of fiction to be quiet, to say, okay, it's a fiction, we don't need to fight, and so forth and so on. And this position, for example, is the one which is defended by Douglas Joseph in this part. I will not read the quote, but if you can read, he says that Leibniz created the notion of fiction as a response to the quarrel in the Académie Royale des Sciences. And thanks to the edition of the Quadratura, we realized that it was not the case at all, that Leibniz thought that they were fiction from the beginning, even before the creation of the differential calculus. So another important publication on this issue was the translation in English by Rick Arthur of some of the texts which were already published in A6.3. And then, of course, the publication of A6.4. In all of these texts, we find that there are some mention of fiction in mathematics concerning infinitely small quantities. And it dates back from 73 and 74. That means that he already has this idea before he creates differential calculus. Okay. So it's not something that was created, not even for differential calculus, and not even to defend differential calculus. This is a position that he had from the start. And he will repeat again and again and again. And what is very interesting is that, in fact, when Leibniz was publicly defended, so these are not public texts, these are notes that he took for himself. The Quadratura was supposed to be a public text, but it was not published, okay? But when he says publicly that infinitesimals are fiction, and typically in the letter, famous letter to Varignon, this is what he says. He says, in fact, I said that to Bernoulli some time ago. So here is the first time where he talks publicly of fiction. It's semi-public, because it's in a letter, and this letter was not supposed to be published. This part of the letter was not supposed to be published. The one before was supposed to be published, but not this one. But he says that he wrote this some years ago to Bernoulli. And we can check if we said that to Bernoulli. And in fact, he said that to Bernoulli in 98 in an exchange which was very important. And look what he's referring to. He's referring to the De Quadratura. So not only we know that Leibniz developed this idea very early, but when he publicly presents them, he says, I said that to Bernoulli. And when he said that to Bernoulli, he said to Bernoulli, in this unpublished manuscript that I had written in 76, I already said that there were fictitious entities. So we have a clear continuity in Leibniz's thought that he developed a strategy at that moment. And this strategy is clearly a strategy which is based on the syncategorematic infinite, that is to say that infinitesimals are just indefinite quantities or finite, variable finite quantities that you can parameterize. So I put here a text which is much later, in which is very clear the way that it works. Indeed, the matter seems to reduce to this. One needs to allow for pure mathematics to be preserved intact from metaphysical controversies. He says that in 76 already. So it's not something that he says during the battle at the Académie Royale. We can do this if caring not at all whether the infinitely and infinitely small in quantities, numbers, and lights are real, we use the infinite and infinitely small as apt expression for condensing thought. So this is the famous compendium cogitation. Thus, it is granted that they are imaginary. So it should be said that imaginary and fictitious are often put by Leibniz on the same, it's the same point. These quantities can nevertheless be employed like the imaginary roots in algebra. And what is important is this. Hence, it follows that this arbitration is never to be used without an explanation of what it is substituted, by which the matter reduced to a rigorous demonstration in the style of Euclid or Archimedes. So here we see clearly the syncategorematic point of view. That is to say that you have to translate the proof into variable finite quantity in the manner of Archimedes, in the manner of the ancients. And this is the method I gave in the Acta Eruditorum when I explained the lemma and comparables. Therefore, when it can be shown that in the assertions of the geometers the error is smaller than any assignable, that is null, we say, by way of abbreviation, that the error or the divergence is infinitely small, and we employ it in our calculus as a quantity. And as a quantity, it's a fiction, it's a fictitious quantity, it's not a quantity. And neglect it in comparison with that of which it is a discrepancy. For the reasoning is immediately made rigorous by changing the indefinitely small into the determinately small. This is a passage from the indefinite to the variable finite quantities, the less than an assigned quantity, which a demonstration shows can be held to be zero, so that the matter reduces in a way to that particular kind of demonstration, examples of which are to be found just about everywhere. So for him, it's just a tradition of doing a demonstration in the manner of the ancients. And this is the principle of the differential calculus. So this is about the syncategorematic infinite, and in fact, this is what he says to Varignon in this letter, which was published, the first letter of February 1702, which was published in March. He says that this is basically the idea of the syncadiomatic infinite, that is to say that you just have to have something which is variable or indefinite, and that's enough for you. I will not, but okay, so that was what I wanted to show or to recall in the first part of the talk. And this, of course, Eberhard Knobloch played a huge role for us to know and to understand. That is to say that Leibniz has this notion of infinite which is based on the syncadiomatic infinite. But I said I will talk about two infinites, syncadiomatic and actual. Okay, and I think that on that point we made some new discoveries. And I will present some discoveries that I made. So, if you think that syncadiomatic means potential, it cannot be actual. Okay? If you think that syncadiomatic means potential, what I have shown is that what you need to do differential calculus according to Leibniz is potential infinite. And this was basically the opinion of everybody, including myself. I even wrote this in a paper, okay, until very recently. That is to say that it seems that Leibniz is defending a potential infinite. The problem is that here he's saying that there is an actual infinite. And the example that he's giving is mathematical. And it is the example of the fact that when I do the Galileo's paradox, if I consider that it's a totum collectivum, I have a contradiction. But if it's a totum distributivum, I don't have a contradiction. And here, says Leibniz, there is an actual infinite. Not a potential one, an actual infinite. So here there is a huge question, is how can he say that there is a syncadiomatic infinite, which usually was considered as being a potential infinite, and actual infinite on the other side in mathematics. And we know by this text, which was already published by Gerhard, that in fact, in this case, in the case that he mentioned to Varignon, that is to say the sum of 1 over 2, 1 over 4, and so forth and so on, here he considered that this is a totum distributivum. If we want this series to converge to 2, we need it to take it as a totum distributivum. That is to say, we need, if we compare with what he says to Debos, an actual infinite. If we want the series to converge to its value, and not to be an indefinite approximation. So here, of course, there is a big question, is how can he say that? It seems to be a contradiction or something. So recently I asked myself, but where did Leibniz take his idea of syncadiomatic infinite? And for example, where does he speak of syncadiomatic infinite outside of these three quotes that I gave, which are the only three quotes that are known, Debos, Varignon, and Nouveau-Dessay, that are the only three quotes. Do we have other places in Leibniz corpus in which Leibniz talk about the syncadiomatic infinite? And there are some, but this passage we have not studied because they are not from Leibniz, they are notes that he took on other authors. Okay? And in fact, there is one very important text that was published in A64, which is a commentary that he wrote on Caramel. And it's a very, very interesting passage, so I will explain to you what it is about. So it's from the text by Caramel. So Caramel was a mathematician, but he was also a logician, but he was also a metaphysician. So it was a very important person who wrote about all kind of stuff. And he wrote this text, which is called Leptotatos, which is a text of metaphysics. And in fact, the place where he talks about syncadiomatic infinite is a place about eternity. And you have all kind of problems with eternity, all kind of paradoxes about eternity, which were very famous. And here is the position that Caramel will defend. He will say that the collection of instants is taken syncategorematically by us, but is categorematic, it's a categorematic infinite in God's formally. Okay? That's the idea. So what does it mean? What is this about? What is the... So the point is the following. If you want to conceive eternity, a very natural way is to say that eternity is a time without beginning and without end. If you did this, what you're doing is what they call imaginary time. It was very well known in the scholastic literature. You just take time and you extend it before and after any end, and you have an infinite time. Okay? This time cannot be God's eternity. Why? Because in God's eternity, there is no before and after. it's not a real eternity. It's an infinite time is a successive order. Okay, and that does not work because in God's eternity there is only one eternity. Okay, so the problem now is so you have this image of eternity, which is what they call imaginary time. This is the syncretegrammatic infinite. But now in God you have the true eternity. The problem is that if you in God you don't have a before and an after, you have only one eternal now. Or that means that you have only one eternal instant. So that means that God cannot say, for example, oh, I will create this at this time or this time, because there is only one now. So the solution that Caramel finds, which is very clever, is to say, in God, there is only one instant when you take it in the absolute, but then you can formally distinguish the instant exactly in the same way that you can formally distinguish the properties of something, even if these properties belong to one and only one essence. That's the idea. So what he says is that the collection of instant is taken syncretegrammatically by us, okay, and it corresponds to a categorematic infinite, but it's the same collection of instant. And why is it very interesting? First, you have somebody saying you can take one and the same infinite collection to be syncretegrammatic or categorematic at the same time. That does not work if it's potential and actual. That does not work, okay? And second, what is very interesting here is that what he proposed is a way in which you see the syncretegrammatic as related to some kind of indefiniteness, okay? And not as a kind of potentiality. And in fact, so here is the passage from Caramel. Here is the note from Leibniz. Here is the passage from Caramel. And in fact, I was able to find a text in which Caramel says syncretegrammatic is not the same than potential infinite. Okay, he was very clear about this. And precisely because you want the syncretegrammatic to be compatible with the actual infinite. I will not explain why, what is the context of this passage, but once again, it's very interesting. I just translated for you the end of the passage, but as I see it, so these people are the Scotists, and the Scotists were defending a view in which potential and actual could be at the same time. But as I see it, they are missing the true concept of the syncretegrammatic infinite. Look, the syncretegrammatic infinite, which is the same as that of indefinite. So this is exactly what we saw in Leibniz. Indeed, a multitude can either be finite, or infinite, or indefinite. It's a third position. Okay? Of this last kind are the multitude of parts which are in Aristotle's continuum. Very interesting. Okay? And the multitude of possible creatures which are in the treasures of omnipotence. So the idea is that, so it's the same kind of problem, that is to say, if you look at all the creatures that God can create, he has to see them all at once, because he sees all of his creation, but he has to see them successively, because he wants to create one, and then the other, because then he creates time, he creates the world. And so it's the same idea, that is to say that you can see the one and the same infinite collection from the syncretegrammatic and the categorematic. And now it's my conclusion. I think I'm fine with time.
5 minutes.
Yeah, good. So here is, I think, a new stuff that I bring into the debate and the discussion. So Leibniz received the notion of the syncretegrammatic through an author, Caramel, who first distinguished the syncretegrammatic and the potential. And I think it's very new. If you read the literature on the syncretegrammatic infinite, everybody conflates the syncretegrammatic and the potential, including what they read like this. Two, he related the syncretegrammatic to the indefinite. It's absolutely explicit. It's the same word that you find in Leibniz. Third, he allowed it to be compatible with the existence of an actual infinite. So this is what we need. This is exactly what we need. The only thing that is different between Leibniz and Caramel is that Leibniz says you cannot call this actual infinite categorematic. Because a categorematic is a totum collectivum, and a totum collectivum can never be non-contradictory. So what Leibniz is doing is just saying the same thing that you did with the syncretegrammatic and the potential, you should do it with the actual and the categorematic, and you should say that one can have a syncatematic and actual infinite, but it will not be categorematic. So I think that this is what I said here. And I will stop here, and I will finish with this picture. We'll talk about this. I think that maybe 10 persons in this room are on this picture, and so you can try to find them. It's not easy. And so, thank you.